I'm Alan Hall, host of the Uptime Wind Energy Podcast. Our guests this week are Hans Loewenheath, Product Manager for Xweather Lightning at Vaisala, and Ryan Saeed, Senior Scientist at Vaisala. If you're not familiar with Vaisala, Vaisala is a global company specializing in environmental and industrial measurement solutions. Founded in 1936 and headquartered in Finland, Vaisala has grown to become a leading provider of reliable and accurate instruments, systems, and services for a wide range of industries and applications. Ryan and Hans, welcome to the program.
Thanks for having us.
Hi, happy to be here.
Just reading some news stories this week, unfortunately, of people attending to a soccer field. They got hit by lightning. And they were clearly out in a time when it wasn't raining, right? This is sort of the clear lightning strike scenario. There's thunder off in the distance, but they don't think twice about it. And next thing you know, you're in an ambulance going to a hospital. And the wind turbine technicians, I think the case is so much more risky because if you're up in a turbine or around turbines are lightning magnets for the most part. And you don't have a lot of advance warning.
That's right. Lightning is chaotic and unpredictable. There's really no safe place to be outside when there's a thunderstorm nearby. A lightning can even strike several miles from the thunderstorm core. There are general guidelines in place that reflect this unpredictable and unsafe environment. The National Lightning Safety Council has a motto: when thunder roars, go indoors, and advise not to return outside for at least 30 minutes after lightning passes by. And so for these reasons, it's really important to be aware of your environment and surroundings, in particular, be able to track thunderstorms in real time.
Right. And what is a safe position? If you're around a wind turbine, where are you going to go? Is the vehicle enough usually?
The safest place to be during a thunderstorm is in a modern building. The electrical wiring and plumbing serves as a Faraday cage, or it safely guides the electrical energy from a lightning flash that hits the building through these wires into the ground. Now, of course, you don't want to be touching any of these wires or plumbing during a thunderstorm. If you can't get to a modern building, an alternative is to find a metal-topped car. So just like within a building, the metal around you will guide the electrical current from a lightning flash safely into the ground. And there too, you don't want to be touching any of the metal parts. Notice I did not mention a wind turbine or a tower as a safe place to be during a thunderstorm.
Yeah, as we have seen, many a lightning strike will cause a wind turbine fire. And you just cannot be in the nacelle or in the tower. You need to be out of there if lightning is around. And I think a lot of times technicians kind of get caught off guard, especially if you're up tower and you're working on a big project and you're not poking your head out once in a while. You may not realize that storm is approaching. That's a serious risk.
It's risky to rely on our human perception to track thunderstorms in real time. Our ability to see lightning or hear thunder could really be compromised, particularly if we are preoccupied doing something else. It's much, much better and safer to have an existing infrastructure in place that can track lightning in real time, regardless of its distance to you, and ideally push an alert to give you a notification if there is thunderstorm activity in your area.
Right. So Hans, there's actual applications. Vaisala offers that as a service, right? So Xweather is a service that Vaisala will provide, and it's easy to go check it out. Just go on the web and look at vaisala.com, and you can get to this information. But I don't think a lot of technicians and even operators have realized that this resource is available yet.
Yeah, this data is available as a service, and it's available directly from Vaisala Xweather, as well as through a number of partners that utilize the data that Xweather provides in their own platform. So it's really, it's really at the fingertips of the technicians today. And this data as a service means that nobody needs to tap in or install any sort of device on site that looks at lightning detections nearby and requiring a piece of hardware to be installed for that in order to keep your people safe. This really is a digital cloud-enabled solution that anybody can utilize today.
Yeah, I think that's the trick here, right? You see these devices, they appear in magazines and online, where you put up a sensor and it has a little light or siren that goes off if there's a quote unquote thunderstorm in the area. Those are not nearly as accurate as what Vaisala delivers in its Xweather system.
Yeah, absolutely. And I want to be clear that we do provide on-site flashing lights and sirens as well, but that's a cloud-enabled device and it's still relying on our owned and operated lightning detection networks in the back end and still providing that last mile delivery as that particular notification channel, as well as SMS or email or other types of notifications. There's all sorts of different notification channels that you can use to make sure you're getting that last mile delivery and ensuring your people are going to a safe place.
The single sensor that you mentioned that provides some awareness of thunderstorm activity in your area, that's certainly better than nothing. But those sensors have their limitations. They work by measuring radio bursts from lightning that are nearby. They measure the direction and estimate the range from the sensor to that lightning activity. And the real challenge is getting that range or the distance from the sensor to the lightning correct. That's very hard to do accurately from a single sensor. And if you don't get that range estimate just right, then that can lead to some inefficiencies or compromised safety for the lightning warning system. A much more robust and precise and reliable method is to use an existing lightning locating and detection system. So our National Lightning Detection Network has an existing infrastructure of very sensitive radio receivers across the United States. And these listen for powerful radio bursts from lightning. A lightning channel is basically a big antenna in the sky that generates a powerful electromagnetic or radio burst. And what we do is we measure the precise time at which this radio burst arrives at each of our sensors. And it's GPS time tagged. And we stream this information back to a central processor and then collate this information from all these sensors in real time in order to then calculate and pinpoint the precise time and location of the lightning discharge all across the US. And in fact, we have a network as well globally that does this at a global scale. And so what we can do is pinpoint lightning within about 100 meters in the US and precise timing. And we do this within 15 seconds or so. So what this means is with our broad network across the US, we can detect and pinpoint lightning in your area often before the thunders even reaches your ears.
That's an amazing system. What drove the development of that system?
We have been operating and refining the National Lightning Detection Network in the US for decades. And in fact, earlier this month, we just celebrated our 40th anniversary for the first lightning flash detected by the network.
Wow.
The development of our lightning detection technology was really driven by two main applications. In the very early days, it was primarily forest fire detection. So using lightning detection as a way to try to detect early when forest fires might start due to natural lightning flashes. The second broad application is in the electric utility sector. The transmission and distribution line operators are really interested in knowing precisely where and when lightning flashes strike their distribution lines, because these can cause electrical faults. And so being able to take appropriate corrective action really depends on knowledge of which of these faults are caused by lightning flashes. Now, this particular application really relies on precise time and location accuracy or location precision of our lightning solutions. And so this is when we developed a technology to locate lightning extremely precisely using GPS timing. And fortuitously, this was also enabled by the emergence of commercially available GPS technology in the early 90s. And of course, we continue to refine this technology to today, driving down to location accuracies of 100 meters or so, which of course is also very helpful for the wind industry as well.
Okay, so you've had about 25, 30 years of this system and being able to finesse this system and tweak this system to what it's at today. I was just on your website earlier today, actually looking at the Xweather system again, and the amount of data that's provided is astounding. So you can tell if a lightning strike is quote unquote positive or negative. You can tell if it's a discharge in the clouds, which is amazing. So you can actually tell what is happening real time and the kind of storms. And I assume a lot of news services use your product. Aviation companies, right? Airlines must use this product. Utilities, as you mentioned. It seems like there's so many applications to know. Insurance companies would be another one, I would think. It seems like it's such a wide use because if you're not there when the lightning strike happened, you wouldn't know in most cases why a fault would occur, even on wind turbines. And I think the wind turbine case is really fascinating because there's a lot of faults that happen that operators don't know why.
That's right. Tracking thunderstorm development and propagation, real-time lightning information is critically important for real-time situational awareness and the lightning safety applications that we've been talking about. And the real-time detection across the US and across the globe really enables precise tracking and improved safety margins for these types of applications. Now, we also have a growing record of every lightning flash that we detect. This record goes back decades in the US and over 10 years globally. And for this record, we keep track of not only the precise time and location of every lightning discharge, but also its strength, an estimate of the number of amps that were lowered to the ground or that flowed through the ground contact point, whether it hit the ground or not, was it a cloud to ground or a cloud discharge, information about how precise we located it, and extra information that help estimate the damage potential for this lightning flash, including the number of current surges that go through a common ground contact point. And all of this information is very helpful for forensic type applications. This includes insurance claims or the fault information that we talked about earlier, or damage potential, for example, to wind turbine assets.
That's one question I get asked quite a bit is how many lightning strikes are over 200,000 amps? Because that's the IEC spec for wind turbines, 200,000 amps. So there's a general assumption like if something happened on a wind turbine, it must have been from really quote unquote strong lightning. 200,000 amps lightning strikes are pretty rare though, right?
The IEC lightning protection system standards are based on an observed distribution of electrical currents in a lightning flash. So for example, they may be pinned to the first percentile or a threshold above which we would only expect about 1% of lightning to occur. So sort of by definition, these very powerful lightning flashes, over 200 kiloamps are relatively rare. But of course, it's important to detect them and report where and when they occur so that corrective action and some sort of maintenance or inspection can occur after that happens. And of course, any lightning flash has the potential to cause damage. So all of them are important to detect and monitor.
Yeah, I think that's key. I think a lot of damage we're seeing in the field are what I call normal lightning strikes in the 10 to 30,000 amp your kind of range. It's enough to do damage to a wind turbine and definitely enough to really hurt a technician. I've heard some discussions from technicians saying, "Oh, these lightning strikes aren't that powerful. Most of them." Like, yeah, it will really mess you up, and if it doesn't kill you, it's going to destroy your nervous system because you're made of water and electricity essentially. And you can't be outside when this is going on. And if you look at some of the Vaisala data on a lightning event, you realize if you put yourself in the middle of some of these storms have thousands of strikes going on around you. It may not seem like it, but there's a lot of electrical activity up in the clouds. that you may not be able to see or notice.
We see only a small fraction of lightning with our eyes and hear a small fraction of thunder with our ears. In fact, about 3/4 of all lightning happens in the thundercloud. That is, it doesn't hit the ground. And you can get really interesting situations too, where large organized systems called mesoscale convective systems can propagate over your area and leave behind it this sort of sheet of charge that can serve as a conduit to guide very powerful and dangerous lightning flashes that may connect to the ground many miles or tens of miles behind the main storm front. And this is one of the reasons why it's advised to wait some amount of time, say 30 minutes, after the lightning flash occurs in your area. And in terms of damage to human life or hazards to human life, the numbers are really scary. The temperature in a lightning channel can exceed several times that of the surface of the sun. So this is many tens of thousands of degrees. And in fact, only a small fraction of injuries and deaths are from direct lightning strikes. You can be injured or killed from the ground currents, or if a lightning flash hits a tree or a structure nearby, from debris from that lightning discharge. So because of the powerful numbers and the huge numbers of voltages and amps involved in a lightning flash, it really is advisable to seek a safe shelter, or if you have to, in a car, anytime there's any risk for a lightning flash in your area.
Yeah, and more recently, I've noticed companies are starting to use your data to determine why technicians may not be working. So if you're an operator and you pay for technicians to work at a site and they're not working, right, they turn in the timesheets and they show downtime. A lot of times they need to justify why. Why were you down? Well, there was lightning in the area. Well, was there lightning in that area? Yes or no? Vaisala gets rid of all that. It tells you, yes, there was lightning in that area, and my technicians were not supposed to be out there. They were following the rules and doing the right thing. And it just clears the air, because without that quality data set, I think a lot of technicians get pressured to be out in places where they shouldn't be. And that's not good for safety. But Vaisala takes all that kind of question mark out of the situation, because the system is so accurate. It's going to lead to safer situations. And I know one of the questions that happened when we were down in New Orleans, someone came up and was asking me about offshore wind. Is the Vaisala data good for offshore, like in the New York Bight area, and then in California, and in Gulf too, where we're going to put wind turbines in the water?
The National Lightning Detection Network that provides the lightning data feed for our Xweather offering has excellent coverage and precision in the US. And this very much extends to 10, 20, 30 kilometers offshore. So the same kind of operational awareness and lightning safety that you might have for operations within the coastal boundaries very much extends to the majority of these offshore installations. Now, as you get farther and farther from the coastline, we then start to fill in with real-time lightning data from our global lightning detection network. Now, this network provides real-time data anywhere on the planet with about a kilometer resolution. And this is still sub-storm cell spatial accuracy. So really, anywhere in the world you are, we can turn on a data feed and provide real-time lightning and thunderstorm awareness that will help you achieve more efficient and safe operations in that area.
And I know every year, Vaisala puts out this really interesting report about lightning strikes all over the world. So sort of a country by country, blow by blow, even state by state, I think in the United States, of where the lightning strikes have occurred, how many. And I think I read the part about the North Pole saying that the North Pole strikes are more recent, that they may be an effect of sort of the warming of the Earth. We're seeing more lightning strikes move towards the pole, which then you have to think, well, if the North Pole is seeing changes, if I'm down in Texas working on wind turbines, I wonder if we're going to see changes in the lightning. Is it going to become more frequent? Or is that some of what the data may be indicating? We're seeing kind of more strikes in different places?
We've been establishing a global record of lightning for just over 10 years now. Now, this isn't long enough to establish a definitive climatological trend, but in those 10 years, we have seen a marked increase in thunderstorm activity at extreme latitudes. And in fact, several years ago, we made it into the Guinness Book of World Records for detecting a lightning flash closest to the North Pole. It was about 33 miles away. And in fact, very recently, lightning was identified as an essential climate variable by the World Meteorological Organization. And Vaisala Xweather is a contributor to that effort to build a growing database of lightning flash occurrence and thunderstorm occurrence for researchers to use and be able to correlate with other climatological trends and variables. And certainly with increasing effects from climate change, we expect thunderstorms to become more severe, weather to be more severe in general, and more unpredictable. So in this changing climate, being able to accurately track and monitor thunderstorm development propagation only becomes increasingly important.
Yeah, lightning is kind of the pulse of the planet in an odd sense. That's what it is. And I've watched some more recent papers being published about pollution in the air. And right now we're having Canadian wildfires just north of us in Massachusetts, and there's a lot of smoke in the air. It seems like there's a connection between sort of particulates in the air and the number of lightning strikes. As the air becomes quote unquote dirtier, there's more particles in the air. There tends to be more lightning strikes. Are you seeing that same sort of data correlate with actual measurements?
There's definitely a possible connection between pollutants and aerosols and thunderstorm development. So what can happen is an increased aerosol concentration in the cloud can suppress rain development. And as a result, more moisture or humidity is released into the surrounding atmosphere. And this in turn creates more favorable conditions for thunderstorm development. So through this kind of mechanism, there's certainly a connection between these two factors. And in fact, there is ongoing research on the climatological scale to try to understand this connection and possibly relate global pollution patterns to thunderstorm occurrence and thunderstorm climatology. Now, of course, there's also a strong connection between lightning and forest fires, which are a major source of pollutants. At least in the US, over half of all acres burned by forest fires are from lightning-initiated forest fires. And then, of course, the pollutants and aerosols as a result of the fire can have effects on weather patterns, and through this other mechanism, an indirect impact on thunderstorm development itself.
And also with wildfires, though, you can have wildfires generating their own lightning without any, precipitation occurring as well, and something called pyrocumulonimbus lightning activity, where, even a wildfire that started from lightning could then grow exponentially to the point where there's so much particulate matter in the air that it generates its own lightning and makes it really difficult to fight that wildfire in a safe manner for firefighters.
Weirdly enough, I was talking to somebody in Western Canada that owns a wind farm, that there's a lot of fires like in the Yukon more recently that seem to be generating lightning strikes off of the fires to turbines. Like you wouldn't think so. There's not a thunderstorm out there necessarily, but they're taking these really odd lightning strikes because of the fires. So there's just the planet is changing in the relations to lightning strikes. I in my lifetime, I think I've noticed it. And the Vaisala data is providing some of that research that's desperately needed to understand how the Earth works, because it's a complicated system, right? The Earth is a complicated system. But the one thing you can repeatedly rely upon to measure are the number of lightning strikes. And Vaisala is key to that.
You can also get lightning events in a wind farm during the wintertime in a snowstorm. So really, for wind farms, lightning detection is a key variable year round.
Winter lightning is a really interesting topic. So typically, winter lightning is relatively rare. There's a term called thunder snow. But what can happen is with a tall object, they can actually initiate their own upward lightning. The reason for this is charge separation happens at a certain temperature range. And during the winter, that temperature range occurs at a much lower altitude. And so there's these charged layers that are closer to these tall objects, like a communications tower, or of course, a wind turbine blade. And so this can promote the initiation of upward lightning. And what we indeed see is there's an increase in these, or there's a high occurrence in some cases of upward lightning from tall towers or wind turbines, of course, after they are installed in some of these winter storms. And this is certainly a phenomena that we're interested in tracking over time and characterizing, and could be a really important factor for optimizing maintenance and inspection schedules. So that's something that we're curious to investigate further going forward.
I think key for operators, it doesn't matter what size of operator you are. You need to know what's happening to your turbines in relation to lightning strikes, and to your technicians. You need to have data. And I've talked to operators that don't have the Vaisala system, and like, at a minimum, right? It's the first easy step. If you can, there's a lot more difficult things you can do. Why not get the Vaisala system and at least know what's happening? Hans, it seems like that should be, we're trying to spread the word to the world that they need to have some insight. And I know the industry, in terms of IEC specifications and things of that sort, are pushing operators to get to that level at a minimum. Does that make sense, right?
Yeah, and what our data really helps operators do is not just keep technicians safe, but also, develop their own inspection procedures and routines, and trying to make this whole industry a lot more efficient. And if you're having to replace blades all the time because you're not having a thorough procedure to go inspect, and the lightning damage can escalate after an individual strike. If we're making this a more inefficient process, and we're not trying to improve that, then this whole green energy push in this wave is going to be a lot more challenging. So with the Vaisala Xweather Lightning data, we can enable operators to really make a much more efficient operation, both on the cost of the maintenance of the turbines and keeping their people safe while still operating efficiently. And reducing those costs overall mean this is a much more financially attractive industry to be in and be a part of, and continue this excellent growth that we've seen so far.
Yeah, well said. And we need to spread that word, and that's what this podcast is about. And that's why I wanted to have both of you on to spread the word. So this is going to be a very fascinating lightning season based on what we just had so far this spring. And I want to have you back. You know what? I want to have you back when you get ready to start publishing your annual summary. Because those things are, if you haven't downloaded that, go to the Vaisala site and download the annual lightning strikes and pick your country and take a look at what's happening around you, because those are just amazing. The data there is astounding. And I've been to some of those other countries that you publish, and I think, man, they have some really strong lightning. I wouldn't have guessed it. Italy, Croatia, Greece, amazing. and to think that one company has ability to monitor around the world is incredible. So Hans and Ryan, thank you for being on the Uptime Podcast. It's been great having you here, and we're going to have you back. I want to learn more about the research going on behind lightning and Xweather.
Happy to be back anytime.
Hey, thanks very much. I really enjoyed being here.
You can learn more about Vaisala Xweather by visiting xweather.com. We'll see you here next week on the Uptime Wind Energy Podcast.